So thanks everyone for coming back to the second day of the workshop. I'm Laszlo Tado from Emory University. I'll be sharing today's session in the morning up until the afternoon, and then Manuel will take over. And it's my great pleasure actually to have a good set of speakers lined up and ready to go. So without getting too much into this, we would like to hand over to the first talk by Rama Cont, who's a professor of mathematical finance at Oxford University. And he has made many contributions to a variety of things, including probability theory, stochastic analysis, math modeling in finance. And today he's going to share some quite exciting results he got on asymptotic analysis of deep ResNets that I'm personally very interested in. And without further ado, okay. If people have questions along the way, you can, I will also handle the Q&A. You can chat with me or I will let Rama decide how he wants to take other questions. So, yeah. Thanks a lot.
Okay, thank you very much, Lars. I'm very pleased to present in this workshop and look forward to feedback from the participants, especially the chairman, who's an expert of this topic. So this is joint work with Alan Cohen from InstaDeep, a tech startup in London, specialized in deep learning, and my colleagues Alain Rossier and Eugène Yuan-Xu from Oxford. The topic of this talk is the asymptotic analysis of deep residual networks in the limit when the number of layers is large. I will briefly introduce residual networks. I guess many people already know about them, and quickly review some previous important work on the link between these networks and certain finite difference schemes of ordinary differential equations. This has led to a lot of exciting developments in the literature on the theory of deep learning, which is very interesting. And then I will describe a little bit a more detailed study of this asymptotic analysis in the deep network limit. First, by showing you some numerical experiments, which suggest some interesting things are going on. And then in the second part, showing you some theoretical results, which explain what we see in these experiments and show us what happens in the deep network limit. And we will see that there are different deep network limits for this class of networks, depending on some features of the architecture. So, what are residual networks? Well, some of you are very familiar with this, but just to make sure, a residual network is a multi-layer feed-forward neural network in which you introduce at each layer what's called a skip connection, which is a fancy word for saying that you're going to add the identity to the output of the layers transfer function. So if you have a feed-forward network and you call f of x the output function for one layer, in the residual network you're going to add this skip connection, which jumps over the layer right to the output, and you're going to add the input itself to the output of the feed-forward network. So it's just, we're going to add the identity to the mapping, which is described by the usual feed-forward network. Okay. Why is this interesting? Well, there's a lot of evidence that this kind of these skip connections do improve the representation of various kinds of data input output maps. And in particular, it's easy to see that, well, in this representation, if you put all the weights to 0, you get the identity. So representing the identity is a trivial issue with this, whereas with the feed-forward networks, for representation of identity, when you look at the conditions in which you have to represent identity are not trivial. So if your map is a perturbation of the identity, this may be a good idea. And well, the main reason we are interested in these networks is that they have been extensively studied in the deep learning literature, and there has been a lot of evidence that this architecture performs very well in certain applications like image recognition. There is this landmark study of He et al. 2016, also Chen et al. 2016, where they train this kind of architecture on ImageNet, and they show that with such architectures, with something like 30 layers, you have a very good representation comparable to other state-of-the-art architectures available at that time. So they perform very well for certain the supervised learning applications. And very importantly, these studies claim that they also address the issue of vanishing or exploding gradients by because when you add the identity, you completely change the nature of the gradient. There's a regularization involved in this in the representation. Adding the identity addresses also this issue of the numerical vanishing or exploding gradients. Okay. So this is just to motivate why people have been studying these a lot. There's a lot of literature on these networks. So now in mathematical terms, what we have is you can represent the network in this way. If we call the HK the hidden state in an L layer neural network, L will always be the number of layers. K is the layer we're looking at. So when you go forward in the network, the hidden state at layer K plus 1 is, well, if you only have the feed-forward network, you have the second term. So there is a multivariate activation function, which I denote sigma d in dimension d. And then you have this multiplication and addition inside. So these are the weights of the networks. And then you can have a multiplication outside. So these are trainable weights. And in the ResNet architecture, you add this first term, which is the identity. Okay, so you start from an input and you iterate this forward to get to layer L, and the layer L will give you the output. HL would be the output. Okay, so this is the representation of the forward dynamics in the network, and the trainable weights are AK, BK, and delta K. Now, why has this been the focus of so much studies in the theoretical literature? Well, because there were two very interesting papers, including one by our chairman, Lars and Eldad Haber in 2018, where they noted that this representation, well, reminds you of a finite difference scheme. And so you can think of it maybe as a discretization of an ODE system, which is the one written here. It would be, and under some conditions, these two things are linked. So it means that if you think of you introduce a fictitious time step that is the number of layers renormalized so that the step size becomes small. For example, this can be 1 over step size. You can think of step size as 1 over number of layers, and then the time goes from 0 to 1. Then you may think of this as a discretization of an ODE. And this has many interesting consequences, because if this relation is good, is one that actually describes the way the network functions, well, then you can map the learning problem for the network to an optimal control problem for an ODE. This point of view has been developed in a series of papers by Wayne and E and co-authors in Princeton. Then the other, I think, one of the interesting ideas in Haber and Rutoto, which I will not develop here, but I think it was a very, it's another direction, which is to use this idea to examine the stability of the network. And also it inspires you to, this is an explicit discretization, what's called an explicit finite difference scheme for this ODE, but as people in numerical analysis know, there are other ways to discretize the same ODE. And they're implicit schemes or implicit explicit schemes, and they have better stability properties. So this is also a very interesting idea which comes out of this link. And I think that's something that was developed by Lars. So there are many reasons to consider this link. And also from a computational point of view. If this ODE essentially gives you the same thing as this discrete network, well, ODEs are well-known things. We can use state-of-art ODE solvers instead of iterating this clumsy equation one. So it gives you many ideas for possibly improving the learning algorithm. And you can also think of this ODE as an efficient representation of equation one, where you have fewer parameters, or just renormalized parameters, homogeneous parameters representing the dynamics of the same network. Okay, but to be fair, these papers, these foundational papers, didn't make any specific claim about the convergence of the one to the other in terms of, you know, a precise convergence result, and this turns out to be a little bit delicate, in fact. So one way to think about the relation between this feed-forward network, this ResNet, and the ODE is to say, well, you know, if I think of time flowing from 0 to 1 and number of layers is L, so I define a time step of 1 over L, then time flows from 0 to 1. Then if I think of this delta K in front of the activation function as something of order 1 over L, then this starts to look like a finite difference scheme, because the step size is in front of it. This looks like an Euler scheme. And indeed, one can show that if the prefactor is of order 1 over L, doesn't have to be precisely 1 over L, and then if the weights inside the activation function, you can think of them as the discretizations of some smooth functions A bar and B bar computed at the points K over L. Then as L increases, you can show that this link is in fact true. The solution of the ResNet dynamics converges to this to the solution of this ODE, and I will give a precise statement later, which is due to, in fact, Thorpe and Van Nip, again, the organizer of our weekly seminar. So, however, this is a typical result you can get from numerical analysis. This is a well-known result for convergence of Euler schemes. But as you note, here we're assuming things about these weights, but in practice, the weights are learned weights. So they result from training. So you don't really get to choose how the weights behave when the number of layers increases. They result from training. So one can deal this in two ways. One can try to first do numerical experiments to see how the actual trained weights behave when you change the number of layers. So we're going to show some controlled numerical experiments for that, and see if these assumptions are satisfied. And there's another way, which I will not get to probably in this talk, which is our current work, which is trying to derive the asymptotics of the trained weights from the specification of the objective function and the training algorithm. So, but in both cases, the trained weights are what they are. You can't really get to specify how they should be, because you don't get to choose the behavior, the asymptotic behavior as L goes to infinity. Now, here are some examples, though, some examples from the numerical experiments we have been doing, which I'm showing you in more detail later, but just to show you that there may be something else going on than just the assumptions that I just outlined, saying that the weights will be smooth functions of the layer. So here are examples of trained weights with different activation functions. So same architecture, but sometimes we use tanh, a smooth activation function, and sometimes we use ReLU, a non-smooth activation function. And what we see is that actually the trained weights, so this on the same data set, we train ResNet architectures just with different activation functions. And here the number of layers is very large, not because we advocate using this number of large layers, just to see what happens when number of layers is large. And what you see is that on the left, for example, you see an example of the dependence of trained weights with respect to the number of layers. with respect to, sorry, the layer. So this is number of layers is fixed, is 9,000. And you have, this is an example of a certain weight. So one of the elements of the matrix A, its dependence with respect to the layer number K. And what you see is that indeed, if in the case of a tanh network, you have a smooth dependence. It is plausible to assume that when the number of layers is large, this is going to be a continuous function, or maybe even a smooth function of the layer. It looks like a smooth function. In the second example, in the middle, you have the same data set, same architecture, but just the ReLU network. And now it looks very different. This doesn't look like a sample from a smooth function. It looks more like a white noise. And in fact, if you resum these, so instead of displaying the weights themselves, you display the cumulative sum of these weights. So again, the trained weights, it's the same quantity as in the first figure, but for ReLU, you see that the cumulative sum of these weights, so the sum of the weights from layer 1 to K, gives you the last figure here, which is looks like something like a diffusion path. So this suggests that in the second case, the ReLU case, same architecture, the limit of the trained weights behaves more like a white noise. Its cumulative sum behaves like a random walk or something like a Brownian motion, but certainly the weights themselves do not converge to, do not look like they converge to a smooth function. So this shows that there is more to it than just this Euler scheme thing, because here we have the same architecture, but in the case of some a smooth activation function, we have a smooth limit for weights. In the non-smooth activation function case, we have a kind of a white noise limit. So there's something going on here, and we would like to understand if this is just an example or it's a systematic effect. So through careful numerical experiments, and then we'll come back to this at the end and show why we should expect different limits, and can we actually derive these limits theoretically. So the outline of this work is the following. In the first part, we investigate the actual behavior of trained weights through detailed numerical experiments, controlled numerical experiments with realistic size ResNet architectures of the same type and architecture that are used in state-of-the-art image recognition. And then, through these numerical experiments, we will identify at least three different scaling regimes for the weights, depending on some properties of the network architecture. You saw that one of them is probably going to be the smoothness of the activation function, but there will be some other properties too. And then we show that under two of these three scaling regimes, the ResNet will, we can show that the ResNet will converge either to an ODE or a stochastic differential equation, depending on some features of the network when the number of networks increases. The third regime being identified as a sparse network, so it's really not like an ODE. Okay, so here, so let me start with the numerical experiment. So basically, the summary is what I showed in the previous slide with the pictures. So in summary, what we find is that for smooth activation functions such as hyperbolic tangent, we observe that for a large number of layers, the weights behave like a smooth function of the layer. So if you display any of the weights in the matrix as a function of the layer, you get things like this. Whereas for ReLU, the non-smooth at zero, the weights behave like a white noise. What does that mean? It means that if we do something which is unnatural operation, probably, which is summing the weights from layer 1 to K, then what you get is that the sum behaves like a random walk in the matrix space, which means it's something like a diffusive thing. And this is a typical example of such a way. Okay, how do we see this? So this is a picture, but how do we actually show that this is the behavior when you do a large number of experiments? Are you going to look at the picture every time? No. A systematic way to do this is to train the weights and then measure certain norms. So here are the norms I'm going to display in the numerical results. So first of all, we're going to look at the magnitude of the weights. So this is the supremum norm of the matrix, which is, so at each layer, we look at the Frobenius norm of the matrix of weights. And then we look at the maximum across layers. So first question is, do the weights shrink to 0 or do they converge to a finite value? Because the ODE limit assumes that the weights somehow converge to a finite value. We'll see that typically the weights may shrink to 0, in fact, as the number of layers increases. Then we look at the norm, the same norm, but now for the cumulative sum of the weights, which is not a natural thing to look at. But if you think of the white noise limit, this is the object that's going to converge, that's not going to blow up. And then we have scaled, then we also look at the smoothness of the weights as a function of the layer. So to look at the smoothness, we look at the size of the increment. So how much does the weight at layer k and k plus 1 differ? And if this is a smooth function, which is have some Hölder continuity of order beta, then this should scale like step size to the power of minus beta. So if you multiply by L to the beta, this should converge to a finite value, not to 0 nor to infinity. So this again gives us how smooth it is as a function of the layer. And finally, if we really think as the picture suggested, that what we're seeing is a diffusion limit, so the weights are have a diffusive behavior as a function of the layer, like a random walk or Brownian motion, then a quantity that will have a well-defined limit is what's called the quadratic variation. So the sum of the squares of these steps. So this is what also we look at. If it's a smooth function, this thing will converge to 0. If it's something like a diffusion, this will have a finite limit. And if it's rougher than a diffusion, this quantity will blow up. So by examining these weights and how they scale as a function of the number of layers for trained weights, we will be able to see what type of smoothness is the natural smoothness to be expected from the learning. Now, note that usually when you train weights, you typically apply a regularization term. You're not just doing the least squares output minimization, but you add a regularization term. And of course, if you add some of these or other stronger norms as regularization terms, like smoothness norms, you may force the weights to be smooth, but at the expense of deteriorating the data fit or the learning performance. So in all the experiments I'm going to show, there's no regularization term. So what we're trying to uncover is the natural smoothness of the trained weights. And of course, this is going to be very helpful for choosing a regularization term, because if you see that the degree of smoothness is something, then if you add a much stronger smoothness term, you may actually distort the learning or you may deteriorate the performance. But if you add the smoothness term, which is in line with the natural smoothness, that's going to be something that is going to work well. So this is useful also from an algorithmic perspective. Okay, so if you follow the pictures that I showed earlier, what we find in the numerical experiments is two types of different behavior. One is smooth behavior, smooth limiting behavior of weights, smoothness of trained weights as a function of layer. And another one is like a diffusive type behavior, random walk type behavior. So we formalize these as two hypotheses. Hypothesis 1 is smooth behavior. Hypothesis 2 is diffusive type behavior. So smooth behavior corresponds to the thing which includes the ODE, the neural ODE limit. So we say, well, if you look at the weight as a function of the as a function of the layer, renormalize so that layer becomes time flowing from 0 to 1, this should have a smooth limit eventually after renormalization by some power of the number of layers. So this allows the weights, individual weights, to shrink to 0, but if you multiply them by, say, square root of L or some power of L, this may have a renormalized weights may have a finite limit. So this includes the case where beta is 0, that will be the neural ODE limit, but it can be more general. And then the second type of situation is when the weights, instead of being samples of a smooth function, are increments of something. So that's very different. So increments of some continuous function, but this continuous function may not be smooth, maybe something like a Brownian motion or a diffusion. So the increments will behave like white noise, but if you resum them, then you get something which has a finite limit. Okay, so very different types of behavior, and these two situations are mutually exclusive if W is non-zero. So they cannot be both samples of a smooth function and increments of some continuous function with shrinking step size. Okay, so to distinguish these two situations, and eventually one can have other situations depending on the scaling that we find, what we do is this: for each depth, so we fix the data set, fix the architecture, and the only thing we vary is the depth of the network. So for each depth, we train a residual network with stochastic gradient descent on this fixed data set until we reach a satisfactory training performance. Then we repeat this for different depth levels L. And then we examine the behavior of the trained weights as a function of L by examining these different norms that I just showed you. And the norms are trying to see whether some property like smoothness of the weights with respect to the layer blows up or stabilizes when the depth increases to large values. And typically, we expect that these norms behave, as I'll show you, these norms will have typically a behavior which is the power of the layer, of the number of layers, and the power will tell us what kind of behavior we have in terms of smoothness. Okay, and as I explained, we look at the norms as a function for the weights itself, also for the increments of the weights. These correspond to two different properties: smoothness and the fact whether the weights themselves blow up or go to zero. So, and also we do it for the cumulative weights. That corresponds to the hypothesis that the weights are the increments of some continuous function. So for each set of trained weights, we look at the cumulative sum of the weights up to layer K. And under hypothesis 2, under the diffusion hypothesis, if you resum the weights, you should get something which, so the resumming averages out the white noise term, and you get something that identifies the smooth component. And also, we isolate if there is a non-smooth component, we can try to assess the degree of non-smoothness of this component by computing the sum of squared weights, which corresponds to the quadratic variation of this non-smooth component. Again, if it's a diffusive type or random walk type behavior, this sum of squared weights will converge to a finite limit, which corresponds to the quadratic variation of this non-smooth component, if it's finite. Okay, now what do the results show? Well, the results, I'm going to display just how these norms vary in terms of the number of layers. So the number of layers is always the horizontal axis. The vertical axis is always one of these norms. So, and all of these are logarithmic plots, double logarithmic plots. So they just display double. So in these plots, a power law behavior will display as a straight line. So first of all, what we see is that the weights always decrease as the number of layers increases. So this means that if you just take the naked weights, they typically converge to zero. And that's not very surprising, because if you have a dense network, and if the input-output function is finite, if you increase the number of weights, each weight has to decrease to zero, because otherwise the contribution of the layers are going to add up and you're going to blow up. So the weights decrease, and in fact they decrease as a power of the number of layers. That is, okay, in this case you see a fit with a power law of 0.7, but okay, I'm not claiming that these values are very precise, but let's say around 1 over square root of L is something that you see. And for the cumulative sum, you see the opposite. So you have an increasing norm for the max, and this is for smooth activation functions. Now,
3 more minutes, Rama.
Okay. Now, if you rescale the weights by the correct exponent that we just saw, then you have a stable limit in the tan H case. So this means that renormalized weights can converge, but the naked weights just go to 0. Now, in the ReLU case, it's very different. In the ReLU case, in fact, what you see is that the weights themselves, they behave like this. They behave like something like an increment of a continuous function, something like a white noise. And what converges when the number of layers increases is what we call the quadratic variation of sum of the squared weights. This suggests really that a diffusive type limit is the relevant limit, because that's what you expect. That's what you expect in that case. And for a smooth function, you would expect that the sum of squared weights goes to 0, and in fact it doesn't. Okay. Now, and in fact, this you could think this noise part, this non-smooth part, is not relevant, but in fact, if you put that to 0 by hand, if you compare the trained network where you remove that noise part, you see that it considerably deteriorates the performance. So it's actually a relevant part of the trained weight. Okay, now if we go back and revisit the neural ODE limit under now these new assumptions and this more detailed assumptions on the scaling of the weights, what does that show us? Well, so here I'm going to give you some of the theoretical results in the paper. So now we, instead of assuming that the prefactor is 1 over L, we allow it to be 1 over L to the power alpha, where alpha can be distinct from 1. In fact, in the numerical experiments, we never see 1. It's something between 0 and 1, something closer to 1/2 than 1. And also we observe that you need a renormalization for the weights, otherwise they shrink to 0. So there's a non-zero exponent here, a beta. And the neural ODE limit I described in the beginning corresponded to alpha equals 1 and beta equals 0, but we don't observe that in the numerical experiments. We observe that both are in between 0 and 1, but the sum is close to 1. So now we're going to examine the limit of this equation when we have descaling assumptions instead of just 0 and 1 for the exponents. And I'm going to show you the results for the case of a smooth activation function, which this is satisfied by tan H, for example. So as I said, the case alpha equals 1 and beta equals 0 corresponds to the neural ODE limit. And this was studied in great detail by Thorpe and Van Gennep. It's a very nice paper. I'm not sure why it's not published. It's a very detailed and beautiful paper, where they show that in fact the hidden layer, the hidden layer, if you look at it as a function of this fictitious time going from 0 to 1, it converges to the solution of this ODE. This is the neural ODE that was introduced in Haber and Clutotto. And the convergence is, in fact, they show a gamma convergence. So it's just not just convergence in the usual sense of finite difference scheme, but if you optimize an objective function for the discrete network, it converges to the solution of the same optimization problem for the ODE. So the learning converges in some sense. So this is a very interesting result, but it describes the case for us, which is alpha equals 1, beta equals 0. And what we observe in the numerical experiment is that we never get those extreme values. On the other hand, if you have alpha and beta that are not 1 or 0, they are in between 1 and 0, but the sum is close to 1, which is the value we observe in the numerical experiment, then you have a very different limit. So what we show is that the hidden state dynamic still converges to the solution of an ODE, but the ODE is very different because now it only involves the gradient of the activation function at 0. So it's insensitive really to the activation function in this limit. It only involves the slope at 0, and it's a linear ODE. So this more general result does not require smoothness of the coefficients. It just, if you have continuity, it's enough. Holder continuity is enough. And more importantly, the activation function doesn't appear at all in the same way as in the neural ODE limit. So the neural ODE limit is somehow a very special limit where you need to fine-tune these two coefficients. And in the generic case of alpha and beta between 0 and 1, whatever value they may have in between 0 and 1, you get this universal limit, which is seems to be very insensitive to the activation function. Now, how about the second case where we get like weights which look like white noise? So the cumulative sum of the weights converges, but not the weights themselves. So in this case, not surprisingly, so I'm going to skip some of the detailed assumptions, but basically here I'm restating the hypothesis 2, the behavior, the diffusive or random walk type behavior of the weights. And the only technical assumption we had is that this is not, so this doesn't have to be really a rounded motion. These W terms can be any Ito process. It doesn't have to be round motion. They don't have to be independent increment random walks in the other. So under in this case, again, without fine-tuning the scaling coefficients, the scaling coefficient alpha and beta can have any value in between 0 and 1, and their sum is equal to 1, as in the experiments. Well, in this case, we have an ODE limit again, and we can show again the uniform convergence in L2 to the solution of the same ODE as in the case of as in the previous case. But in the case where alpha equals 0, meaning that in the case where the prefactor is not shrinking to 0, okay, what we see is the emergence of another limit. So this is like, and this is a stochastic differential equation limit. So in the case where alpha is equal to 0 and the exponent beta, so the weights shrink to 0 with some exponent. That's what we observe in all the numerical experiments. Then we observe ODE, an SDE limit. So there is this non-trivial white noise term which appears in the dynamics. And this is very different from the ODE limit I showed in the previous slide, because this is now an additive multiplicative differential equation. So there's an additive term, the white noise term, and there's a multiplicative term, where you have white noise multiplied by this. And this seems like a very simple equation, but in fact, combining the additive and multiplicative term in the same equation leads to a high level of expressivity, which, you know, people have been studying this in other related work, especially the group of Teichmann in Zurich. This leads to, I mean, unlike the linear ODE, which is not very expressive, as you can imagine, this one has you can express a great number of functions as solutions of additive multiplicative ODEs, SDs. So here, unlike the ODE neural ODE limit, in which the weights appear as coefficients of an ODE, of which the solution is the hidden state, here the weight appears as the driving noise in the ODE. So it's a very different way for the weights to appear. The weights are the WAs here, the hidden state is the solution, while the weights appear not as coefficients, but as the driving noise in the ODE. I'm going to end here, just so just to note that the notion of convergence used in these results is strong convergence, which means that we're not showing a convergence of averages across many trained networks, which is what's called weak convergence, which was studied in some previous studies like Peluchetti and Pavaro. But we show what we show is almost sure convergence. So any typical realization of the weights, initial weights, will lead to the same type of outcome. Okay, and one can confirm, one can go back from these theoretical results to the numerical experiments and compare the results found in numerical experiments with the limits derived from these results, and confirming numerically that the networks do behave like the suggested limits in the limit of large depth. So I'm going to end with this. So what we've tried to describe is some numerical and theoretical analysis of ResNets when the number of layers is large. We identify 3 scaling regimes for the trained weights. I only showed you 2. The third one is the sparse regime, which we describe in the paper, but I didn't have time to describe here. And what we show is that there's not just a unique neural OD limit. There are several possible limiting ODs or SDs, depending in particular on the smoothness of the activation function and some other features of the network. And in each of these regimes, we're able to show strong convergence of the hidden state dynamics to these OD or SD limits. Thank you.
Well, thank you, Rama, for this exciting talk. I'm sure there are maybe some immediate questions. So Stefan just wrote one in the chat window. I can read it. So Rama, do you have any intuition why already a single non-smooth point, such as in ReLU, can cause such a dramatic change in the weight limit behavior?
Yes, that's a very good question. Well, an important thing which we saw in the results is that as the number of layers increases, the weights themselves shrink to zero. So the norm of the weight at each layer shrinks to zero. Because each individual weight shrinks to zero, when you look at the equation describing the dynamics, what you see is that only the behavior near zero. So we see the weights inside shrink to zero. So only the behavior of the activation function at zero is going to determine what's going to happen. So the smoothness only matters at zero. Because in fact, the way you prove these convergence results is basically you do a Taylor expansion at zero, and then you control the remainders. So the behavior at zero is what's going to determine. What the activation function does away from zero doesn't matter here in these limits. And that's very different from the neural OD limit, because in the neural OD limit, the entire activation function appears. And that's because there's the assumption that the weights do not shrink to zero. They have a non-zero limit without renormalization. We don't see that in the numerical experiment. This is a very important question.
Yeah, there's another question by Mehmet about testing results in your simulations, which probably refers to a test loss, otherwise please correct me. And also whether or not we can take alpha and beta equal to 1/2 all the time for ReLU. Would that be your recommendation?
Well, I mean, we don't observe exactly 1/2, but as I tried to show in the results, 1/2 or 0.55 or 0.7 from the theoretical point of view don't make a big difference. They lead to the same type of limit. Of course, quantitatively they're different, but the main thing is alpha equals 0, or is it somewhere in between 0 and 1? That makes a big difference. But 1/2 or 1/2 plus or minus epsilon doesn't change the qualitative nature of the limit. But yeah, I think it's a 1/2 is something easy to derive from a diffusion model. So you can think of 1/2 as a work horse to try out ideas here.
Chandra also has a very interesting question. Does the scaling result of the trained weights depend on how you initialize the network, or what algorithms are used to train the weights?
Well, so in all the examples, I didn't show all the examples here. There are more examples in the paper, in particular with the convolutional architectures and so on. So in all the examples, the weights are initialized as IID. So this is a very common thing that is used in many papers. So the weights are initialized as independent Gaussian weights. And in fact, if you think about this initialization, it corresponds to a white noise already. Okay, so if you want to get something different from a white noise limit, the training really has to change the nature of smoothness of the weights. But if you think about the IID weights, corresponds to not a function of a layer, but white noise. And then the training is done in all cases with stochastic gradient descent with the same hyperparameters that are described in all cases. They're described in more detail in the paper. I don't know if that's the question or something else. but there's no regularization used in the training, because that would, of course, distort the smoothness norms that we're trying to assess. That's an important detail.
Yeah. I'm sure there are more questions, and I would probably suggest, Rama, if you have more time to stay on, but I know that in Cambridge, for the lucky few people who made it there, there's some coffee waiting. So we should probably give them a chance, and also give all of us a chance to thank you again for this fantastic talk. And I certainly also would appreciate some more discussion. Can I ask you a few questions also? So the ones that were already in the chat room were on my list as well. So one I had was, so since the training problem really is difficult in my experience, because we have a very non-convex and reluctant, also non-smooth objective function and so on. Like, kind of, how confident are you that these things are, are they well trained? I mean, I'm sure you kind of look at these things, but
well, I mean, so again, in the paper you can see more details on training and the training performance, but our goal is to assess the scaling behavior of trained weights. This is the whole point, because if the training can change the nature of the weights, and that's what we want to assess. So the protocol we adopted here is, again, to train all these networks on the same data set, and we train them to get the same level of accuracy on the data set. So we are comparing things that have comparable accuracy. And in order to be able to see the effect of depth in the training, the data set has to be sophisticated enough so that actually the increasing the depth has some impact on the accuracy. So what we did use is, so we have two examples in the paper. There's three examples. There's a simulated data set, then there is a MNIST data set, and then we use also a standardized data set of images. So we use these three examples. The data sets are sophisticated enough so that the depth has some interest in the application involved. Now, we also check these results on different initializations of weights, because the claim we make is that there is strong convergence. So it's not just for a particular realization. We're claiming that the results, the asymptotic results, should hold for any typical realization drawn from an ensemble. So we do these IID weights and initial weights, and we retrain to see if the qualitative behavior of the trained weights is different or not. So that's described. That's what I meant by controlled numerical experiments. It's not just like one example and we try to draw a conclusion from that. So I don't know if that answers your question.
Oh, I mean,
but I think the real underlying question is, can we derive the scaling behavior of the weights rather than assume it and then derive the limit? And that's what we're doing now. There is some hope for doing that, because basically it all relates to the behavior of these smoothness norms under a gradient descent. If you do a gradient descent, what happens at each step of the gradient descent to these smoothness norms? If you're able to show some inequality, such and such smoothness norm increases or decreases at each step of gradient descent, then it suggests that some smoothness norms will go to zero, some of them will blow to infinity, and so on. And so there is some scope for doing this, where we have some partial results in this direction. I didn't have time to describe them here, but we're not at the stage where we can derive the scaling limit from the architecture and the features of the data set, but there is some indication as which type of smoothness norm will be increasing or decreasing along the gradient descent.
Yeah, no, I mean, definitely, I think it's like you've done what you can do, I think, in this case, with all the checks and balances. One thing, kind of from my experience, though, I mean, I, for example, would like never recommend an IID initialization when I have a network with a few thousand layers. So in your case, I'm actually super impressed that for the 10H, you get some weights that are smooth. That to me was
well, yeah, because
you initialize them completely.
The initialization is really not smooth.
Yeah, so exactly. I would typically, in my experience, is actually, or my experiments typically initialize them constant in time. So I just have one random matrix that I then keep constant, just to make sure, sort of, also that the dynamic system makes at least some sense. Although you may have noticed in our works that we're not really working too much on the continuous level anymore compared to neural ODEs. So in the end of the day, I think most of these things live in a discrete, the interesting parts live in a discrete way, just
yeah, well, I mean, you're right. I mean, we're not claiming that this particular initialization, we're not advocating.
No.
Neither the ODEs are showed in the limit nor the particular initialization as efficient algorithms for learning. What we're saying is that, okay, if you use this is the limit you get. Is it good or not? That's a different question.
Yeah, and it's
you've investigated that.
And of course, it's what most people are doing. So, or what most people are using. So that's why.
But it is very important. It is very important here. It is very important here because basically the bounded motions or diffusions you get here, the W's, are nothing else but reshuffled cumulative sums of these weights.
Yeah.
So if you don't have IID weights, you'll never get these things.
Learning is the thing where it's like, oh, we don't know.
I mean, it's
learning is the magic.
Really interesting. I'm really motivated to look more into the technology. I think it's really relevant because in most cases, people just draw the weights IID and yeah, kind of go there.
You started on. Did you do anything with that? No.
Rama, I also had another question. I think you've answered it already with your response to Mehmet's question. So is it, I was wondering at some point in the talk if the behavior you see is because of the smoothness or the different smoothness of 10H and ReLU versus boundedness.
Right.
10H is bounded. Training.
Well, yeah, that's a good question. The numerical experiments don't show that, but okay, I think we're hearing the coffee breaks.
We are not getting coffee. That's so unfair.
Okay, but it's in the theoretical results I showed, we don't need boundedness. The only thing we need on the activation function is smoothness and a bounded third derivative.
Yeah.
And TANH works, but that's all, because basically the weights, only the behavior near zero enters the equation, so we don't really need global boundedness.
Yeah, that's what I meant. That you sort of answered that then.
But the third regime in which I did not describe is a sparse regime. Mm-hmm. So when we look at the ResNet architecture with convolutional layers, so that's very commonly used also for image recognition, in fact, that's done in detail in the paper. There we see a different regime, and that's a sparse regime where actually a few weights are non-zero, they have non-zero values, and the rest are very close to zero. So that has been studied a lot, in particular by Stéphane Mallat and his group. They try to link these convolutional networks, the behavior of the convolutional networks under learning with wavelet representations. So this is a very interesting direction, and we do observe that, and that doesn't correspond to an ODE or SD limit. And there, that's where the weights are not shrinking to zero, and so that's where the global properties of the activation function do matter. It's like you end up with a few layers that are relevant, most layers are irrelevant. And so you end up with a behavior, although the network is deep, in fact, it behaves like a shallow network with selective weights being non-zero. So that's a very different regime, which also has been observed in in applications in image recognition as being web relevant. So I didn't talk about it, but I think that might even be more relevant for this type of application than what we're doing here.
Yeah, I mean, more to learn from the paper about that. But that's definitely something to look at, I think. Great. Can you help us move on to the next speaker, Rama? And
okay, so shall I just unshare?
Yeah, that's the hard part as a chair. You have to always interrupt when it's getting interesting.
Thank you. So,
Yuguan, do you want to go ahead and try your screen share? Oh, he's here. And there is another question, Rama, in the chat window for you. See if you can answer that in the chat or.
okay. So